Today we're going to be proving the statement for every integer a, if a squared plus 2a plus 1 is even, then a is odd. This statement is actually a conditional statement of the form if P, then Q. And this can be logically expressed as P implies Q. You'll notice this where P is called the hypothesis, Q is called the conclusion. And so you'll notice that this hypothesis is more complicated than the conclusion, especially when it comes to mathematically expressing it. So today we're going to prove the contrapositive, which is logically equivalent to this implication P implies Q, but expressed a little differently. And so the contrapositive not Q implies not P is logically equivalent, like I said, to P implies Q. And so how would we express this? Well, this is Q, so not Q is A is not odd, not P is A squared plus 2A plus 1 is not even. And this can be written as for every integer A, if A is not odd, also known as even, then A squared plus 2A plus 1 is odd. So we're going to start with our hypothesis, our conclusion. So by proving the contrapositive, we're going to have to assume that this hypothesis is true and show a form of logical statements that leads to not P, right? And so we're going to start with not Q and follow some logical series of steps where S is a statement that's either true or false, but not both. R is also the same. And finally, we're going to end up with something that looks like not P. And obviously, there was going to be more steps in between, but this is just kind of showing you the path we're going to be taking. And so we're going to begin the proof now. And the easiest way to begin the proof is to simply begin the proof. And I'm letting the audience know what's happening. It's very important to let your audience reading this know what's happening. So you just say, begin proof. And we're going to say, suppose an integer A is even. Then we can express A equals 2k for some integer k. Right? This is the definition of what it means to be even. So now we're trying to get from this hypothesis to this conclusion. So what we're going to do is we're going to algebraically manipulate A so that it looks like that. We're just going to say, next, multiply A by A, then add 2 multiplied by A, and finally, add 1. This looks like A squared plus 2A plus 1. A multiplied by A, we're adding 2 multiplied by A, and we're adding 1. Notice that we've declared A to be equal to 2k. So we can say by substitution, we can say A squared plus 2A plus 1 is equal to 2k squared plus 2k plus 1. We can simplify this a little bit. We can rewrite it. We can condense it or simply rewrite it. By rewriting equation, we obtain a squared plus 2a plus 1 is equal to 4k squared plus, that should be 2 times 2k, pardon, 2a times 2k, plus 4k, let me fix that, 4k plus 1. Pardon the bad handwriting there. Now, we can redistribute, right? We can distribute the 2 out of here, right? Factor for some, and we're going to distribute by the property of distributivity. So by distributivity, the expression (4k squared plus 4k plus 1) is equal to 2 times 2k squared plus 2k plus 1. And if you multiply the 2 back in, it becomes apparent that this is equal to that. So, because the integers are closed under addition as well as multiplication, is common, this expression, the expression 2k squared plus 2k is some integer L. So once more using substitution, we obtain that a squared plus 2a plus 1 is equal to 2 times L plus 1, right? Where this is 2L plus 1. I can erase that and make that look a little bit neater there. So I say 2 times L plus 1. This, if you know your definitions, is an odd integer. By definition of an odd integer, we can say a squared plus 2a plus 1 is an odd integer. So notice that we started with a is even, a equals 2k, and through a series of logical steps, we have showed that a squared plus 2a plus 1 is odd, thus proving the contrapositive. And so I'm going to put a little box check mark showing that we've completed the proof. So lets the audience, the reader, know we're done proving this. And by proving the contrapositive, we have thus by default proved that it's logically equivalent. Implication P implies Q is also been proven to be true. Thank you.